All right, so I am just getting ready. Oh. All right, so I'm just getting ready for the class. We still got about 2 minutes before we are going to start with the content. Okay, so what we'll do today, the first thing is I am going to do the lab on Tuesday because I got quite a few questions about it, and so I just kind of decided to honor one of the requests, which is basically to explain it and kind of demonstrate how it is done. So that's one thing that I'll do today. And as I'm doing it, I am going to basically demonstrate how to do homework assignments, where to find the material and how to read the modules. So there we go. All right, so I'm going to get LogicSim started because I'll need that for the homework assignment. And we still got about 1 minute to go, which means somebody is going to turn in the lab like within this minute. All right, so let me go back to the assignment first, or the lab that is due at 7 o'clock, which is another 42 seconds or so. All right, so let me go ahead and put this into its own tab. There we go. And we got 20 seconds to go. Got to be on time, right? I went on a tour in Europe once, and we went to Switzerland, and there's a complimentary continental breakfast at 8 o'clock in the morning. And guess when they start to let people in? It's 8 o'clock sharp. Not a second before and not a second after. And then when we went to Italy, well, let's just say that time warps a little bit in Italy. All right, cool. So let's go ahead and get started with this lab. So I would do it in a way, where I was kind of explain, how to get it done. Okay. All right, so let's go ahead and take a look at the whole thing. I will do it the same way that you guys would. Yes, most people say that the way I word things is weird. I don't know, maybe it's just the way I think is weird, because the words are really just kind of just following the thoughts, right? Okay, so create a main circuit. So you have to go to LogicSim, start a main circuit, and then we're going to have a 3-pin input pin connected to a tunnel called X, another one go to Y, and yet another one go to K0. So let's go to LogicSim. So we are already in the main circuit, and so now we can just go ahead and slap a few pins here. And then we can always change the number of bits of the pins a little bit later. So this one is supposed to be a 3-bit pin labeled X. This one here is also a 3-bit pin labeled Y this time. And the last one is labeled K0, I think. Let me just double check. Yep, it's labeled K0. There we go. And I'll check the text channel in just a little bit. Oh, okay, well that's good. That means you're getting a really good deal out of the tuition fees, because you're paying only for one and you're getting 3 semesters out of it. And we are only in week, I think this is the end of week 3. Yep. So you're getting a super good deal out of the whole thing. Yeah, I am shameless. All right, so here we got some tunnels. So with tunnels, the data bit or the width has to match the wire that connects to it. So if this is a 3-bit tunnel, we have to make sure that it's 3-bit wide. And then we also have Y, which is also 3-bit wide. Now with tunnels, the thing about tunnels is the label, the so-called label, is actually significant. It is not only for display purposes, but it's actually for logically indicating what is connected. Okay, I'm just looking at the text channel a little bit. Okay, so when we get there, I'll talk about it. So this one is called K0, but it's a single bit. So now we can make the connections, just draw the wires between the pin and the tunnel. All right, so we got one part done. And look up the library reference to answer the following question. What is the purpose of the label of a tunnel? There may be multiple correct answers. Select all correct answers. So with questions like this, there are only, let me see, 2 to the power of 4, which is 16 possible ways to answer, even though these are multiple choices. In other words, you can actually select multiple checkboxes, but there are only 16 of them. So if somebody wants to brute force this, because you can turn this in as many times as you want to. So each time you turn it in, it will only let you know whether it's correct or not. It won't actually give you the correct answer. So you can actually go ahead and brute force the whole thing. Yep. Okay, so I'm just taking a quick look at the text channel. But I'm focusing on getting this lab done. So it is displayed as a visual label. A tunnel with a label automatically connects to components other than tunnels of the same name. That is not true. The label is only used when a circuit is printed. That is also not true because of the word only in here. And then the last one is it identifies connectivity between individual tunnel instances, as tunnel instances of the same name are logically connected. So definitely true in this case. It is displayed as a visual label. It is true too. And the second one is actually not true. So if I do not have the wire, the input pin that is labeled X is logically not connected to the label, to the tunnel, which is also labeled X. So I think it is these two. We'll see, when I turn it in, right? Okay, so we are now moving on to question number 2, and let's go ahead and work on this one because this is the one where I get the most questions about. Okay, all right, so I'm just going to read the question just as you will. Now use the following as a starting point of another part of this main circuit. So do not build another circuit. This is a continuation of what we have already. So we have the tunnels, and this time the heading or the facing of the tunnel is different. So we'll go ahead and create that, and then we got 3 more tunnels on the other side. We got P, G, and Q on this side, and then we have 3 gates over here too. Each gate has 2 input pins. So we'll go ahead and just replicate that design. So there's one little trick you can do is you can actually select, copy, move, okay, and then you can flip the facing all at the same time. So you can flip the facing out even when they're all selected. So now it's easy to kind of have the X, Y, and K0 tunnels done. And then we'll have, oh, okay, I got these extra ones that I don't need. So we'll get rid of those. And now we're going to create the P, G, and Q tunnels. So we got, so they're all 3-bit wide. So that means we will just go ahead and make it 3 here. And then I will duplicate like that. So P, G, and Q. All right. So let's go ahead and label P, G, and Q. Oops. over here. So I'm for the time being, I'm ignoring the text channel, just because I'm focusing on working on this in Logisim. So whatever you guys type in the text channel will be ignored for the time being. I'll get back to it when I'm done with this step. Okay. So now we have 3 gates. Okay. So I did not indicate which one is which one, but I'm guessing that most of you can match the shape, from the tool in Logisim. So we'll just go ahead and match the shapes. So we got one that looks like this, and we want to turn it into the narrow shape with only 2 inputs. Now, in order to make sure that these do not give us a problem in terms of number of bits, they all need to be 3-bit wide. So that's one of the issues. But I'm hoping nobody has this issue, because we have the previous assignment of using multi-bit gates already. So we got one like this, and then we got one that looks like this. Okay, so once again, change it to a narrow shape. I believe you might be able to put all of them in and change these attributes all at the same time, but they are not of the same kind of gate, so I'm not really sure whether that will work or not. This works for sure though. So number of bits is 3. I think I forgot to change one of them to 3 bits. Yep, this one needs to change to 3 bits too, and then this one needs to change to 2 inputs and change the size to a narrow shape like so. And then we go back here, we got this, and that. Okay, so we have this one as the bottom one, and then we got this one as the middle one, and then we got this one as the top one. Okay, so now we go back to the text and find out what we are supposed to do. Note that the direction of the tunnel can be changed like most components. So I think by this time you already know, what is the direction, or quote-unquote facing, of a particular component, and you can change it so that the connection point is to the east instead of the default of to the west. The gates next to the tunnels on the right-hand side may not be correct for that particular gate. In other words, it means this particular gate may not be for this tunnel. This gate may not be for this tunnel, and this gate may not be for that tunnel. I'm not sure whether you guys get what I was trying to express, but yeah, that's kind of how I put it. All right. Your first job is to move the gates or tunnels to the right so that the correct gate lines up with the correct tunnel. So we just want to line them up, and we're supposed to move the gates, not the tunnels. So leave the tunnels in place like that. If you don't know which gate is which gate, look up the gates library part of the library reference of Logisim. So you don't really need to do that, because if you look at the toolbox, where you can pull these components out of, it pretty much tells you which one is which one. The shape tells you that this is an AND gate, which is this one here. It tells you that this is an OR gate, and this is an exclusive OR gate. Okay. So now we continue with reading this stuff here. Connect the tunnel from the left to the inputs of the gates. If a particular tunnel is not used as an input, leave it alone. That is basically referring to K0, but we'll see that K0 is not used in any one of these. Connect the output of each gate to the appropriate tunnel to the right-hand side. Okay, but since they're already aligned, so they should all connect. So P, G, and Q correspond to the constructs of the same name, but in lowercase. So this is actually giving you a lot of clues of what you should be looking for in the module, in the binary adding notes. So it even tells you which module you need to go to. It's basically just short of giving you a hyperlink to that particular module. But I think you guys can find it, so I did not include a hyperlink. When this is done, use the poking tool to specify 001 to input pin X, 100 to input pin Y. K0 is not used, so it can be anything. So I have, in other words, I just answered my own question. Okay, which input is not used? It's already written in the same in the question. It answers a part of it. Okay, it's already stated here that K0 is not used, so it can be anything. All right. Now use the poke tool to click the wire connecting to the tunnel labeled Q. Blah 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 blah. Okay, so we'll do that later. So now the question is, okay, what is P, what is G, and what is Q? So I'm not accusing anyone of being lazy and not reading anything, but it is possible that you have read the module, but somehow it did not occur to you that there are definitions of these terms. Okay, so I'm guessing that is the case because I know, some of the people who ask me questions, seem to have read the notes already. It's just that they couldn't find the appropriate definitions. All right, so I'm going into the module so that I can point out where those definitions are. Okay, so we are talking about binary addition, which is here. So open a new tab, and it opened it all the way over here. Okay, that's fine. All right. So let's do the easy ones first. Okay, P and G are the easy ones. Why? Because in the lecture, in the actual lecture on last Thursday, I specifically mentioned that section 6 looks like it is just a kind of an after note. Okay, it doesn't seem important here because it always says is, but wait, there's more. I remember I even compared this phrase to infomercials. Whenever they say, but wait, there's more, there's a lot more, right? Okay. Yes, Aaron, each lab can be potentially different from another lab. Yes, I randomized these things too. Yeah, it took me a lot of work to make that happen, but it was kind of fun, for me to make that happen. All right. But getting back to here, okay, so you guys might want to pay attention of why some of you are missing it. Okay, so this is the paragraph where P and G are defined. Okay, this paragraph right here. Okay, and I remember that I even made a point last Thursday, which is obviously is a long time ago because it is 7 days or 168 hours ago. So that's a long time. There are a lot of milliseconds and nanoseconds in between. But I distinctly remembered, and it was recorded on YouTube, that don't ignore the significance of this paragraph because this is where G and P are defined. So G of I is defined as xi, yi, and P of I is defined as xi plus yi. But what seems like multiplication is not multiplication. What seems like addition is not addition. That was also pointed out multiple times last Thursday because these are all Boolean expressions. So these are actually conjunction and disjunction respectively. So G is using conjunction, P is using disjunction. All right. Now, somebody may ask, but you never mentioned anything like this, so you would use this notation. Well, actually I did. It was way earlier, okay, that I mentioned the notation. I think I mentioned that notation when I explained the definition of Q, which is really handy because that's what we need to do is to define what is R, right? So we can see the definition of Q is right here. Q of I is the result of, calling result in this case is really just the word result. It's the result of R of xi, yi, okay? But in the case of binary, okay, so we generalize to any base and then we specialize back into binary when we get to section 5. So when we get to section 5, I'm just skipping along and define Rxy is x naught y plus not xy. So in this case, I explain exclamation x is the negation of x. The plus symbol means disjunction, logical OR in Boolean algebra. The priority of the operation is negation goes first, conjunction is second, and then disjunction is last. Let's see. I think there's a place I also mentioned. Oh, right here. So the conjunction is explained up here. We define C of xy, which is the carry of adding x and y. That is defined as xy. The notation of multiplication, because that's how we usually write multiplication without the actual times symbol, means conjunction in Boolean algebra. So right here it explains the meaning of the operators. So I borrowed the operators from normal arithmetics simply because it is a whole lot easier to type compared to using the inverted V for conjunction and then the V shape for disjunction. So this is just a whole lot easier to type when I have a plain text editor. Okay. Now, what about R? What about Q of I? Okay. Qi is R of xi yi, and this is how we define R of xi. R of xy, and it's kind of complicated because you need negation, you need conjunction, and you also need disjunction. However, if you read a little bit later, okay, I'm just looking at, okay, I'm just going to cheat a little bit about this one. And, okay, right here. All right, so read this part here. The other one is a little harder. Rxy equals to 1 in two cases when x and y are different. Technically, there is a Boolean operator called, can I get drum roll? Oh? Exclusive OR, and that does exactly this. All right, thank you, Tom. I can hear the drum already, that's good. So this is what I do not intentionally hide things in my notes, okay? That was never the intention. Because if I actually tried, then you guys would not, it would be much more difficult to find it, okay? So there was no intention to hide the definition. But this means that when you're reading the notes, you kind of have to read it carefully. You're not reading a novel. This is not, Harry Potter, okay? You cannot just read the important words and then understand how the story is going, okay? Because this is actually technical, it's in computer science, which is basically a branch of mathematics. So that basically means just about every single word is important. So that means you have to read really carefully and don't speed read through the text, okay? Whenever you see the word define, okay, like here, okay, and there are multiple defines, and you guys know how to use a browser to find words inside a document. So whenever you see define, you probably want to write your own notes, okay, either on the side of a PDF or have your own Google document, or however you want to take notes, okay? You can use just paper and pencil, okay? Doesn't matter how. But you might want to put all the definitions in the same spot, okay? So this way you can kind of easily look through all the definitions and find out how something is defined, okay? Or how I use a particular notation. Because when I explain things, in the notes, I kind of sprinkle things around. I only talk about it when it is needed, okay? I don't just go, in section 1 and I say, these are all the notations utilized here. Because if I did that, it's not going to do us any good, because I would explain that. And most people, by the time we get to use the notation, would have forgotten about the definition of the notation. So I only define the notation when we get to the place where we need to use the notation. But if you want to have your own catalog of how those definitions are, if you want to keep track of all the definitions, then it is handy to have your own notes on the side, on your own little book or in your own document to define all of these terms. All right. So getting back to Logisim, now we know how to reorder things, and I think I'm supposed to only reorder the gates but not the tunnels. So that means P is going to use the OR gate. G is going to use the AND gate, and then Q is going to use the exclusive OR gate. So that pretty much answers the question, and then the connections are pretty easy because X and Y go to all three gates. So X goes to one pin of the OR gate, one pin of the AND gate, and also one pin of the exclusive OR gate. And then Y also basically goes to the other pin of every single gate. Like so. And also like that. And then the output of each gate goes to the respective tunnel that has the name of the result of that particular gate. Oh, okay. All right. So now we are moving on to answer the rest of that question. Okay, so the question says, use the poking tool to specify 001 to X, 100 to Y, and yours can be different, okay, because I have variations of these questions. So we go to X, it's supposed to be 001, so I only have to flip this one, that 0, and flip it into a 1, and for Y we flip this 1 into a 0, okay? And then following even more instruction, okay? Now use the poke tool to click the wire connecting to the tunnel labeled Q. All right, so we go to, okay, this is the tunnel labeled Q. This is the wire connecting to the tunnel labeled Q. Click on it. So now it gives me 101. So now we go back to the question. What is the second number to the right of the slash? Okay, so after you click, you can see that there are two numbers here, 101, a slash, and then another digit over here. I'm assuming you guys have not played around with the default settings. So that means I think this one is already altered, so you're not going to get the same thing. So the unaltered version, okay, let me go to the unaltered version because I have to reset the options of the project to the default because I have changed mine already. The way I change mine is to change, okay, that's, no, that is not the place. I think it's under simulate. Nope, under window. Preferences, yep, I think I changed it here. Window layout. There we go. Okay, so I changed mine already. If you have not changed yours, which I have not told you guys to change it yet, so it's going to display a negative value. So 101 is displayed as -3, and I just want the number to the right hand side, which is this number is the right hand side of the slash. So I go back to my question and then just type -3. There we go. All right. Shall we move on, or are you guys okay? Because I think most questions were related to number 2. I'm just waiting for responses. Okay, Kwan is writing something, and okay, yeah, we can go over number 3, sure. All right, so here's number 3. Number 3 says, now that you have all the bits needed to compute the carry bits, let's start with a new circuit K1. This means you need to use project, on the menu bar and then add circuit to create a new circuit in Logisim and then name the new circuit K1. Okay, and new is actually in italic, which means do not rename main to K1. Okay, so let's go ahead and do just that step. So we go to project, we say add circuit, and the new circuit name is K1. Click OK. Now we have a new circuit. All right. So now we get back to the instructions. To make the main circuit simple and clean, use multi-bit input pins P and G in the K1 circuit. So that means, in the K1 circuit, we need input pins of P and G, and they have to be multi-bit. So now we go back into here, we pull the default pins in first, and then we can change the properties later. Okay, so we need 3 pins if you read the instructions, because we need P, G, and K0. P is multi-bit. It is supposed to be 3-bit wide and labeled P. Now, whether you label this one or not doesn't really matter. Remember, the label of a pin doesn't really mean anything. It's only for display purposes. So this is Q, and this one here is K0. All right. Excuse me. So now we got the pins. Okay. You also need K0 as an input pin, so we got that. Q or G. Oh, you're right. Okay, it's G. There we go. Thank you. All right. Then split P and G to the bits that you need to compute K1 using the carry look-ahead mechanism. Refer to the binary addition module for the exact formula. Using the split end of the splitter, connect bits to the corresponding AND gates if they are needed. The output of the AND gates should connect to the input of the inputs of a single OR gate. So you're only supposed to have one single OR gate. You may have one or more AND gates, okay, because I use /gates here. Connect the output of the OR gate to the 1-bit output pin called K1. Okay, so we'll go ahead and do just that. Okay, so now we pull an output pin, just stick it somewhere, on the right hand side, and we'll call this K1. All right, so here is the part where you have to look up how K1 is defined in the carry look ahead manner. So we now switch back to the notes. Okay, the notes is right here, and the definition of K1 is right here. Okay, so this is how K1 is defined in the carry look ahead manner. So K1 is G0 or P0 and K0. Okay, so we want to replicate this in the circuit. Now, given my really poor memory, okay, even though I wrote all this stuff here, I cannot remember it. Okay, well, that's partially why I wrote it, right? Because I knew that I would forget it. All right, so we're gonna keep an eye on the equation, or we can just use text here to kind of replicate the equation. So this way we don't have to go back and forth between two windows. So we say K1 is G0 or P0 K0. Okay, so this is better because now I don't have to flip-flop between two different screens. All right, so well, we have a problem because this is a 3-bit port. Okay, so if I draw a wire out, this is a 3-bit wire. I don't need all three bits of that. Same thing with this one. This one is good, okay, because it is a single bit. So in order to only get to G0 and also only get to P0, okay, there are several ways to do it. Okay, it depends on how ugly you want your picture to look like. Okay, if you don't mind ugliness, okay, which is fine because I never really said anything about whether your diagram is supposed to look pretty or not, and pretty is not needed. Okay, this class is not about making your circuit look pretty. It is about the concepts behind the whole thing. Okay, so here's a splitter, and in this case I would make sure that we have a 3-bit splitter because otherwise they would not connect. Well, it would connect, but it would complain that there's a difference in terms of the bit width. Okay, so now we have a 3-bit splitter, and because I'm super lazy, I'll just say give me all 3 bits. Okay, that's perfectly okay. Okay, just get all 3 bits and do the same thing with G. Okay, so now we have 3 bits, all 3 bits of P, all 3 bits, individual bits of G. Now, just because I have access to P1 and P2 doesn't mean that I have to use them, right? I can just leave it dangling and go like, nah, not in this picture. I don't need those particular pins or those particular bits. Same thing go for G1 and G2, okay? So now we look at the equation. G0 is all by itself to the OR gate, and then P0 needs to be ANDed with K0. So we do need an AND gate after all. So we pull an AND gate out, and then do the usual thing, making it smaller, and only limit to 2 inputs, like so. And single bit is fine, okay? We are only ANDing 2 individual bits, okay? So it is a 1-bit conjunction gate. And we have to make sure that we are connecting the right bits to this conjunction. The first one is coming from P0, and then the second one is coming from K0, like so. All right. And then G0 is on its own, okay? We don't need to do anything about this one, so this is on its own. And G0 is ORed with the conjunction of P0, K0. So now we need to get an OR gate. So here's an OR gate right here. Do exactly the same thing, change the size of it, change the number of inputs all the way to 2, down to 2. Okay, and you can put it anywhere you want. I mean, I'm just putting it here because it's convenient. Okay, connect these two, and then take the output and connect the output to K1, and voila, we are done with K1. But we're not done with the question. So getting back to the question, okay. All right, so we are done with what goes here. Edit the appearance of this circuit to identify P, Q, K0, and K1. So now we go back to LogicSim, switch to the appearance of a circuit, and just use the text tool to label P, Q, not Q, I keep saying cube, it's G, okay, K0 and K1. All right, so Daniel is, wouldn't you get rid of the extra forks? You mean the extra tines on the fork? I don't have any extra fork, I just have extra ends of the fork not being used. Or is leaving those pins open? Yeah, the pointy bits. I like that. Okay, so there, if you want it to look better, yes, we can do that, and I can go back and show you guys how to do that. But before I forget, I'm gonna get this part done first, and then we can go back and make it look pretty. All right. So here's K1. K1 is gonna have to stay outside, and then we go back to here. All right, so let's go back inside and look at the splitters, okay? I'm pretty sure I talked about this already too. It's just that we talked about it kind of early on. So when you look at a splitter like this, okay, you can see how bit 1 and bit 2 are not used, and same with this one here. So one thing you can do is to change the fan out to just 1, okay? But when you do that, we're gonna have some orange wires, okay? But it's okay, we can fix those later. Oh, okay, maybe not, because it changed the size of the splitter, so we don't end up with a problem. Okay, so we can just now say, okay, that connects here, but we have a problem, because now we have one single output which has all the input bits. All 3 input bits are now at this particular split end, because right here we are telling the splitter that bit 0 has to go to the top, bit 1 has to go to the top, bit 2 also has to go to the top. So what we need to do is to say, hey, bit 1, you're not needed, go nowhere. Bit 2, you're also not needed, go nowhere. So that's how we can make the splitter or splitters look nice, but it is not necessary. Okay, so you guys can choose to do it this way, which looks kind of nice, or you can do it this way, which is a little bit faster, because you don't have to go back and reconfigure your splitter after changing the bit width of the splitter. So are we good so far, or do you guys have any questions about what I have done up to this point? All right, so I'm not getting any questions, not getting any comments of, okay, very good. Okay, so let's go back to the question. To test your circuit, see that the output K1 is 1 if and only if two of the following inputs are 1s, X0, Y0, K0. Yes, this means you have to connect an instance of the K1 circuit to the main circuit, connect PG and K0 correctly, then use the poke tool to adjust the multi-bit input pins X, Y, or the single input pin K0 to test the output of the K1 circuit. Okay, so this part has nothing that you have to show me, but it really is just telling you how you can test the circuit. The next part does require an answer. How many AND gates are needed in the circuit K1 to compute K1? So there are two K1s here. The first one is referring to the name of the circuit. The second one is referring to the actual bit that we want, okay? So this means do not include the AND gates to compute P, N, or G from XY, because those are all done in the main circuit. It is not a part of K1 itself. So if I switch back into the K1 circuit, I can only see one AND gate. So the answer to that question, I'm just going to pick 1 here, okay, because it seems to make sense. Well, since we're in question number 3, might as well just go for question number 4, right? So in question number 4, you're asked, okay, now that you can create a subcircuit for K1, do the same with K2 and K3 using their carry look-ahead formulae. Note that all 3 circuits should use PG and K0 as inputs. This step may take a little longer because K2 and K3 are distinct from K1 and increasingly complex. So that means if anyone is reusing K1 over and over again, something is not right, okay? The equations of K2 and K3 can also be found in the notes. Once you have the K values, what else do you need to compute the sum S bits, okay? So let's go ahead and create the K2 and the K3 circuits, okay? So I'm switching back to here, to Logisim, and I'm going to try my best to do the least amount of work, okay? So we look at K1 and right click, and there's no copy and paste here. Well, that's fine. So we go to project, we say add circuit. This time we are going to add, let's work K3, okay? Because if I can work with K3, it kind of follows that, you know, K2 can be done easier, right? So let's work it with K3. So K3 is its own circuit, but guess what? It's going to have the same input pins and kind of the same output pin as K1. Why don't we just kind of copy it first, right? Copy whatever we can and then change whatever we need to. Okay, so I'm going to just Control select, Control C, go to the new circuit, Control V, and now we have a whole lot of stuff that we don't have to do over and over again. So now we go to K1 and say, nope, this is not K1, this is K3 because we are working with the K3 circuit. The equation is also not quite that simple anymore. So this is important, okay, because I will bet you that somebody used the wrong equation, even though I made a point when I was lecturing and say, okay, you know, somebody's going to get this wrong, please use the last portion of the derivation, okay? Yes, we're skipping K2 because it's too easy. Anyway, we only want to do the hard stuff in this class, okay? We don't want to do the easy stuff. But only I get that option, unfortunately, not for you guys. Okay. So here's K3, and I remember very distinctly last Thursday that I said, okay, there will be a question, you know, that you need to refer to the definition of K3. Don't use this one. Instead, use the last one, because otherwise, what is the whole point of deriving it, right? Okay, so use the most spelled out version. This is the version that we want. This is also the version where we can parallelize the most to get the best speed out of the circuit. That is why we expand everything out, is so that we can have parallel circuits doing computations at exactly the same time. Okay. So I'm hoping that nobody used this definition and then try to connect K2 into the circuit of K3, because that would be considered an incorrect answer. Okay. All right. So let's go ahead and copy this equation or this expression into Logisim, then we'll work with Logisim. Okay, this is going to be the last. I mean, it's going to be the slightly more difficult part of this assignment or this lab. All right, so we'll go back to here, and let's see. I think we can change the text. Yep. Okay, so let's see if we can do that. Yep. All right, so this time we're working with K3. K3 looks a little bit ugly. Okay, it is G2 or P2 and G1 or P2, P1, G0. They're all ended together, or P2, P1, P0, K0. Okay, so it's just a little bit more complex than the other one. Nonetheless, it's completely doable. All right, so now what we need to do is to kind of get rid of all the gates, okay, because we're going to need different gates in this case. So get rid of all the gates, get rid of this wire, get rid of this wire, get rid of this wire, and then turn this one back into a fan out of 3, because we need all 3 bits this time. Okay, all right, so we'll work on this 1 bit at a time. Okay, we'll need a 1, 2, 3, 4 input OR gate as the final output. So we pick out an OR gate. Okay, and well, this time you can probably keep the size, but we still need to change the number of inputs to 4. Okay, like so, and we'll just kind of clean this up a little bit, move this one onto this side, and then move this one over here. All right, so now we have a 4 input OR gate, and we'll just work on this expression from left to right. Okay, so we know that G2 is needed, but it doesn't have to go through any AND gate whatsoever. So this one just goes straight into one of the inputs of the OR gate. Doesn't matter which one, because OR is commutative. Okay, so that means ordering is not important. All right, so that's done. And then the second one is P2 and G1. So we pull out an AND gate. Okay, and I'm going to change the shape so we can make it a little bit smaller, and it will only need 2 inputs this time. And we look at the 2 inputs. One is G1 and the other one is P2. So we can stash this. I'm just thinking about where to stash it. Okay. Yeah, I suppose we can stash it here. I haven't decided yet. It's hard to decide. We can put it here, maybe. Yeah, I think we can put it here. Yes, I just did something that is kind of infamous of INTPs. If you have done your personality test, INTPs are known to be very indecisive on certain things. There we go. This one goes into this pin. Cool. Oh, okay. So now the next one is a 3 input AND gate. So with a 3 input AND gate, I can just duplicate the original, the 2 input AND gate, and just change the number of inputs to 3. Okay, like so. Oh, by the way, you can label gates too. So if you want to specify what this gate is actually doing, you can actually put a label within the gate itself, as kind of like a self-documenting mechanism. But I'm not going to do that because it just looks kind of ugly like that. Okay, so we are working on this one, which takes P2, P1, and G0. Okay, all right. So we'll take P2, okay, which is this one. It takes P1, which is this one. I mean, I'm pretty sure most of you know, what we need to do, for the rest of this thing, but I'm just going to do the whole thing anyway. So we have G0, and okay, we can do this. There we go. All right, so we have the second gate done, and this is the last AND gate. Okay, so the last AND gate needs K0, P0, P1, and P2. So we basically need all 3 of the P bits and K0. All right, so let's go ahead and make a 4 input AND gate, like so. And now we just need to connect all 3 wires to the first 3, and then K0 to the last one. All right, and I kind of need to keep an eye out for the connection to the big OR gate. So I'm gonna have to move it a little bit up here. Okay, so we connect all the P bits first. Okay, ooh, nice. They kind of align right here, right? Okay. That was not by design, trust me. I never design things like this. If it looks nice, that means tech did not design it. All right, so now we got the 3 AND gate. So we just need to hook up the output of the AND gates to the input of the OR gate in any way you want. Okay, whatever looks nice to you is fine, because OR is commutative. Okay, so now we got this circuit done, and we just need to go back to the appearance. Okay, and once again, we just need to label P, G, K0, and also a K3 this time, and move the text to the correct place. We got the P, we got the G, we got the K0, and the K3, like so. Okay, now we can switch back to the circuit because I have one point to make. So now the question is, what if you did not use this particular order, P being the top, G being the middle, K0 being the bottom? If you change this order, then the appearance would also have these pins changed as well. So the way you label the appearance has to match the actual circuit itself, because if you reorder these pins or the positioning of these pins, then their relative position in the packaging or the appearance will also change. So you kind of keep that in mind. All right, so let's go back to the quiz and see if we can just kind of finish it. So once you have all the K values, what else do you need to compute the sum, the S bits? Okay, well, it's multiple choice, so that makes it kind of really easy, right? Because you just have to look up the definition of the sum, the S bits, and you'll find that the sum bits are the R of the K and the Q bits, right? So the correct answer is the Q intermediate sums. Okay. Yes, I'm pretty sure that is actually in the notes too. So we are done, and you just have to make sure that you save the circuit, because the lab that I'm releasing tonight relies on the lab that you just did on the other day. And the answer is no, I am not going to save my circuit and make it available to you. If you want to remake your circuit based on what I have talked about tonight, you are going to have to do it yourself. Okay? I do not mind if you redo your circuit based on what I have demonstrated tonight. That is not a problem. But using my solution as the basis of your next lab is not something that I will support. So you guys will, if you want to use my demonstration tonight as the basis of the lab starting tonight, please repeat the whole process and make that circuit yourself. All right. So are there any questions other than why are you so mean? Okay, I got the opposite. It is not being mean. I think the process of doing this is educational. If not for anything else, you get more familiar with Logisim, the tool, and also, while you're doing that, you kind of get this, you get a better idea of why carry look-ahead is so useful. Okay, let me just kind of go back to the circuit, particularly K3. Remember what I said about we can perform simultaneous calculations at the same time? That's exactly what I mean here. Okay, when you look at this AND gate, this AND gate, and this AND gate, they can all perform operations at exactly the same time. In other words, as soon as the bits, the P, G, and K0 bits change, all three AND gates will basically update their output at exactly the same time. So all three will be done at the same time, and then the OR gate can do its job and do the disjunction of the AND gate and also G2 this time, by itself, in order to give us K3. So not counting the propagational delay to get to the P and the G bits, we only need 1-2 propagational delay to get to K3. But K4 would need exactly the same amount of time, even though the circuit is going to look uglier, okay? But it's going to take exactly the same amount of time. If you look at K1, okay, it looks really simple, but it's going to take exactly the same amount of time because we still need to wait for this AND gate to be done in order for this OR gate to start its operation. So we are still looking at only 2 propagational delay when we are looking at K1, and K3 just looks a lot more complicated, but when you're looking at how much time it takes to complete the calculation, it takes the same amount of time. All right, so I'm getting to the text channel. Tom is asking, is carry ahead related to big O? You can always find correlation. Big O is a notation that talks about how something scales. Okay, particularly in this case, I would assume that the number of bits that we are adding is n. So and what we want to use the big O notation to do is to figure out perhaps how much time it takes to finish the calculation. And in that case, it's going to be big O of 1 because it's constant time. The amount of time it takes to finish the addition using the carry look ahead mechanism is constant time. It doesn't matter how many bits we're adding, it still takes the same amount of time. On the other hand, if you're looking at the number of gates that we need to use, I think in this case it would be to the square of the number of bits that we're adding. So it would be big O of n squared when you want to consider the number of gates that we are using. All right, and then Dawu is asking why we do not the error message that bit width don't match together. I mean in AND and OR gate. All right, so I'm going to interpret this as why are we not getting the error message of bit width don't match when we specify the AND and the OR gate in here. I'm not quite sure what that we is referring to. Are you also referring to what I did here, or just what happens when you did it? Okay. Okay. Well, because these are individual bits already, the splitter convert a 3-bit wire into 3 1-bit wires. So all of these are single bits already, and because all of these gates are by default, only using, they're all by default 1-bit gates, and that's why we don't have a problem. So the splitter is super important, in these circuitry. All right, cool. Oh, haven't done row yet. Okay, so today's row is related to the topic that I was hoping that I could get to, which I am going to get into now. The word is negative. Okay. So secret is splitter. I'm not sure whether that's really a secret or not. I think here, based on the previous lab, the multi-bit gate lab, that's how we started to learn how to use splitters. I think we use splitters actually in the first lab using Logisim. So the concept of splitter has been floating around for some time already. How come we didn't use a splitter to the main? Oh, well, that's the whole point of the main, is that we don't have to use a splitter. So in the main, what we are doing, when we are ready to make all the circuits, this is what we'll do. Okay, we pull K1. Okay, and here's K1, and then what we do is, okay, I'm gonna do this. Okay, copy and paste, or duplicate in this case. Change the facing. There we go. And put it over here. So the idea is, in the main circuit, this is a 3-bit tunnel. This is a 3-bit pin. Well, we don't have a problem connecting these two, right? Once again, we have a 3-bit tunnel and a 3-bit pin. Don't have a problem connecting these two. Here's K0. Finally, we get to use K0. That's how we make use of K1. How do you make use of K3? Same deal. Okay, here's K3. P goes to P. G goes to G. And you got it. K0 goes to K0. That's how we get to K3. Now, I don't have a K2, but you can kind of imagine that it's going to look exactly the same, right? So that is why I put all the splitters into the K1, K2, and K3 circuit, so that the main circuit looks super clean. I don't need no stinking splitters in the main, in the main circuit. Except I actually do. Okay, so tonight's lab is gonna contradict what I just said. You need one single splitter, but doing the role of a merger in the main circuit. Okay, so that's just, but there's only one. Okay, instead of having a crazy picture like this, okay, in main looks relatively clean. Okay, things are relatively easy to see how things are connected. All right. Tom says time to be confused with part 2. Yes. Okay. Is this how the complex chip developed? Okay. All right. So the complex chip is not hand drawn. Okay? We are using pictures to draw, how things are connected. And you can kind of imagine that by the time we get to K64, you probably don't want to do it by hand, okay? Because that's going to look really, really ugly, okay? Because K64 has 63 AND gates and one single OR gate at the very end, okay? And then the connectivity. I mean, just imagine the splitters, okay? Just imagine. Every input, every P, every G it splits into 64 bits, and then the 64 bits fly everywhere within the subcircuit. Okay, it's not like you cannot do it. It's just not feasible. Okay, it's not something that you want to do by hand, and that's why we have. I think I introduced concept before. That's why we have HDLs. Okay, hardware description languages. And there are two main HDLs used in industry. One is called Verilog. Oh, I have a typo. So Verilog is the correct term. Okay, there we go. So if you go to Verilog, you can kind of get a glimpse of the syntax. Verilog looks a whole lot like C, but it's a textual language to describe, what gates you need and how the gates are connected using their designated, pins. So it is a far more flexible way to describe the circuit, because we can now use loops, okay, to specify the connectivity between the AND gates and the OR gates, which also brings us back to the equation at the end of section 6. Okay, so go to section 6, go to the very end. Okay, remember this kind of horrendous thing that we looked at? That can turn into loops, and those loops can then specify how input pins, output pins, AND gates, and OR gates are connected. And you can now, because the loop, the structure of the loop does not change whether n is a large number or not. So once you have the loops in place, you can now say, okay, give me K128, and it will just spew out the connectivity specification between the gates, the input pins, and also the output pins, and then that in return is taken by what we call a silicon compiler. So the silicon compiler will look at the connectivity between the gates and actually turn that into the silicon design on an actual chip. So there's a lot of steps in between, and there's a lot of quote unquote black magic involved. And those are all trade secrets, okay? So Intel and AMD, they both die to try to find out what the black magic is from each other. But that's basically what we call a silicon compiler, and Verilog is the front end. Okay, it allows you to specify code in C, in a C-like language, and then it cranks out the quote-unquote object file from this compiler. Is basically a lower level specification of how gates are connected, and then that specification gets compiled again by a silicon compiler to actually crank out what type of how the connectivity of the transistors, and then from there you have a router to basically to try to figure out how to route electrical signals between the transistors, and then after that you actually get to the die design. Okay, basically it's those are layers upon layers upon layers of different material on a chip, on the silicon die. And then we are ready for fabrication. You send that specification to a fab lab, and then the fab lab will create the actual chip. Yeah. Well, if any one of you is inspired to go to UC Berkeley for their ECS bachelor's degree, your final year project, unless they have changed, is to they will give you a basic design of a processor, and throughout the semester you are going to add more and more features to make the processor faster, and so on and so forth. So by the end of that project, you are going to end up with an actual semi-industrial usable kind of processor. And I think they still use Verilog, but I could be wrong. They might be using VHDL instead, which is the other HDL language used in industry. Yeah, it is pretty cool. A lot of times, we focus only on the software, and we're kind of forgetting about software is running on top of hardware, and hardware is actually really important. For those of you who are gamers out there, you probably can understand and realize how important hardware is when it comes to rendering. Okay, your graphics card has a whole bunch of GPUs, and making the GPUs consume less electricity and consume less power, and therefore you can put more of the GPUs without using a lot of power and have problems dissipating the heat. Those are all really realistic issues that people have to deal with. Another really big application of chip design is Google. Okay, so when you use Google Voice command, when you talk to Google, hey Google, and then do something, and I'm pretty sure my phone is not paying attention to me. That stuff is done by quote unquote neural nets. Okay. And you can do neural nets completely in software using a general purpose processor. You can do it, okay? It's doable. However, if Google is to do that using general purpose processors to perform massive neural network calculations, it would not have enough real estate to house that much processing resources, okay? So as a result, what Google did was they actually designed a chip that lends itself to performing very efficient and high-speed neural net calculations. You can look it up. You can actually just Google it. Okay, just Google for Google neural net chip. Okay, and you'll find articles that talk about it. And because of these special purpose chips, Google was able to shrink down, how much real estate it needs to house all of its servers. And because without these special purpose chips and just use general purpose processors, it would take a whole lot more hardware to perform the same kind of calculation. Oh, okay. I did not know the Design Hub has one of those from Intel. Okay, pretty cool. The GPUs that you have on your graphics card can be repurposed to do neural net calculations really fast. So a lot of neural net computation engines would actually be able to utilize, if you have a graphics card and you say, okay, use the GPUs on my graphics card for faster neural net computation, it will speed up the computations to no end compared to just using your main processor for those calculations. All right, so this is all kind of really interesting stuff. We are only touching the very surface of integrating hardware and software design, because even if you can do something in software, it doesn't mean it's the most efficient way to do it. If you can have specialized hardware to perform the same thing, a lot of times you're saving time and you're also saving a lot of energy, which translates to you can house more computational power within the same footprint of a building. So that is actually what most data centers are pushing for. All right, cool. It is difficult not to copy Randy Schuster. When I've been around for him for a little bit, for long enough, I start to copy the way he talks. It doesn't seem to work the other way around for some strange reasons. All right, so what we're gonna do now, okay, let me check the time. We got 10 minutes left, okay, so we can at least get to the conceptual part of today's topic, okay, the new topic of today. So we are pretty much done with subtraction already, and today's row-taking word is negative, and that's because I want to get to signed value representation. So let's go ahead and just click on it, and I'll give you an overview in 10 minutes about what this is all about, okay? All right, so recall that we have physical quantities, like voltages, and then we have physical devices like transistors, okay? Sort of, okay, Daniel, sort of, okay? Because the whole concept is, the whole idea is, how do we represent a negative value? We don't have a problem representing non-negative integers, right? Because we know how to use different bits to mean the quantities of different powers of 2, so we don't have a problem with that. But now the question is, well, but that is not going to work with negative numbers. So as it turns out, okay, this is the one day that I did not set up a circle, okay. So the thing about negative numbers is there are alternatives to represent negative numbers. In other words, very early on, some people say, well, why don't we use a particular bit and use it to indicate the sign of the magnitude, okay? So we use one bit to indicate the sign, and then the rest of the bits to indicate the magnitude. That seems really logical, okay? That seems like a very logical use of zeros and ones in order to represent negative values. But that approach has one problem. The problem is, if you use that method to represent negative values, then you cannot reuse the adder and the subtractor circuits that we have talked about to perform addition and subtraction, okay? Which is a bummer, right? Because, do you want to waste additional silicon in order to just so that you can deal with negative values? Well, if we can avoid that, we would like to avoid it, okay? So the idea is, let's avoid it, okay? I don't have my tablet set up in a tablet mode, so I can't really draw stuff easily. I'll give it a try, but it may not work. Oh, okay, I see what I can do. Let me go to graphics and then go to Inkscape. Okay, so I think Inkscape can probably do this. Okay, first of all, I have to resize the whole thing. I'm just about to draw something, but since freehand drawing is not easy, for something like this, Inkscape is a really good tool to use for this purpose. Okay. All right, so let's go ahead and focus on just a portion of this area. Unfortunately, Inkscape is not really designed to be used on a small screen, which is kind of what we're dealing with here. Okay, so there we go. All right, so I'm hoping all of you know how to do. Oh, okay, yeah. Inkscape outputs SVG or scalable vector graphics, and that's what the laser cutters use to specify, how to move the laser, on the XY table. Yeah, so it's kind of cool. Inkscape is really useful for many, many different things, but I'm just using it for one little thing right now. So I just want to draw a circle. Okay, so let me draw a circle, and I need to change how I fill the colors and stuff like that. Yeah, so this is going to take a little bit of time because I did not set up my tablet where I can just use a pen to draw freehand. So this is going to take a little bit of time so I can configure everything to work. So I want it not to fill. I want stroke to be black. Okay, that's good. And then I just need to put numbers on it. Okay. All right, so this is all good. Let me go to the text tool and specify a font size of 9. Okay, that looks too small. Okay, maybe 12. Okay, 12 looks good. All right, so I'm pretty sure most of you are familiar with the concept of a number line, right? So when we think about integers, it is a number on a number line. Then you can think of 0 as quote unquote the center, right, of the number line. And then you have positive numbers going usually on the right hand side, and negative numbers usually going on the negative side. So but the line goes stretch on forever in both directions. Okay, but when we actually represent values using bits, it is no longer a number line. Instead, it is a number circle. So if I look at just how we can use 3 bits, okay, 3 individual bits, then we can represent 0. This is where 2 is going to be. This is where 4 is going to be. And this is where 6 is going to be. And this is where 1 is going to be. This is where 3 is going to be. This is 5. And here is 7. Okay. These are all in base 10. So in base 2, this is 0, 0, 0. This is 0, 0, 1. This is 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0. This is 1, 0, 1. This is 1, 1, 0. And this one is 1, 1, 1. Okay. So nothing about this number circle should be mysterious to us at this point, okay? Because we have already talked about base conversion. So if you do a base conversion from 7 to base 2, it will convert into 1, 1, 1 in base 2. So there should be nothing surprising here. So when you look at the number wheel as opposed to a number line, the tricky part is what happens when you add 1 to 7. If you have a number line of natural numbers and you say, I want to add 1 to 7, you get to 8, okay? No problem. But in the number circle, there's no 8 on the circle. So when you add 1 to 7, you get back to 0. Okay, so everything is modulus 8 when you only have 3 bits. Okay, you're basically taking the remainder of whatever operation, addition or subtraction, and you're taking the result and you say, well, the value may exceed what we can represent, but if I mod 8 first, then we can go back and represent the result in 3 bits. That's how we do things, when we represent numbers. So this is a number circle given only 3 bits, okay? The complication is, what about negative numbers, okay? So when you look at 2, okay, 2 is right here, and you say, what is 1 less than 2? Oh, that's 1. But where's 1? You have to go counterclockwise by one slot, right? So if you go counterclockwise, you get to a number that is smaller. So yeah, so if I go from 2 to 1, that's just counterclockwise by one slot. If I go counterclockwise one slot more, then we get to 0. Okay, so that part still works. Okay, except instead of going left and right on the number line, now we have to say clockwise versus counterclockwise. So the thing is, if I have to designate a particular place for -1, it's going to be counterclockwise one slot from 0, which is here. Okay, so I'm going to put the really confusing thing here. Okay, and I'm going to say -1 goes here. And if I go counterclockwise one more from -1, I should get to -2. So -2 really should be here, and -3 should be here, and then -4 should be here. And that's where I stop. The reason why I stop here is not because of time. Okay, we still got a minute to go, or close to 2 minutes. I stop here because now we have equal numbers of values that are negative and those that are non-negative. In other words, if I draw a line, okay, so let me get to the line drawing tool. This is a pencil, this is a pen. I think the pen is probably better. So if I draw a line, stretching from here down to here, okay, one side, the right hand side, are the non-negative values. Okay, so 0 is only counted as a non-negative value for this discussion. And then on the other side, on the left hand side, we have all the negative values, and we have the same number in this case. There are 4, 1/2 of the 8 that are non-negative, and then the other half are negative. Okay, so now the question is, okay, we don't have a problem of 0, 1, 2, and 3, because whether we need to represent negative values or not, those 4 stay the same. The problem is about 7 and -1, because 1, 1, 1 is the representation for both of them. In other words, 7 is represented as 1, 1, 1, given that we can only use 3 bits, but -1 as a value is also represented by 1, 1, 1 in base 2 when we only have 3 bits to represent values. So now an obvious but misguided question is, okay, so this is a question, so and I will ask it, and then I'll explain what I think of it. Okay, so a common but misguided question is, so which one is it? Okay, if I look at 1, 1, 1 as a base 2 representation, then which value is it representing? Is it representing 7, or is it representing -1? Here's my answer to that question, and you guys may or may not like it. Okay, most people would hate it. Okay, my answer is, why do you care? What is it to you? Why do you care? Well, I care because I need to use this value for something. Okay, what do you need to use it for so that you need to know whether it is 7 or -1? That is the question. Okay, why do you care? I know we are running out of time today. Okay, we are 1 minute past, but just to give this class even more value, to kind of echo what Daniel said earlier, that he aged by 3 semesters up to this point of this class. I'm gonna give you some extra value now. Okay, so the question is, why do you care? Because as it turns out that I'll explain next Tuesday, it doesn't matter. Okay, it doesn't matter for the purposes of adding and subtracting. Okay, if you represent, if 110 is representing -2, and you add it to 010, which is representing 2, you actually get to 0. Okay, it is not a problem. Okay, exactly. So it is the context. So now the question is, under which context is it important for me to know whether 111 is representing -1 or is it representing 7? The only context that makes whether the only context that we need to differentiate between -1 and 7 is when we compare. not when we assign, because assignment operations is nothing more than just copying, okay? So when we copy, it's just like, okay, we just copy 111 from here to there. We are done, okay? I don't care what 111 is representing. I just want to replicate the bit pattern from here to there. Not a problem. Assignment doesn't care. As it turns out, addition and subtraction does not care either, okay? Because this representation, and I'm hoping you guys would read over the weekend, this particular module that is called signed number representation. So if you read that, you will know that, hey, addition works the same way, subtraction works exactly the same way. It doesn't make any difference. So the only time it makes a difference is when I need to ask you this question. When I ask, is 111 greater than or equal to 001? Then you need to come back to me and say, Tag, that's a trick question, okay? Because at that time, you need to say, Tag, are you meaning -1 when you say 111, or are you meaning 7 when you say 111? Because now it changes the output of the comparison. Exactly, Tom is right. So only when you compare, you need to know whether it is signed or unsigned. But for calculations, for addition and subtraction, it doesn't matter, okay? We will illustrate all of this and also look at, what is exactly 2's complement on next Tuesday. I'm hoping you guys will have time, after you do the row taking activity and after you do the lab, that you will have time to read ahead of me so that by the time we get to Tuesday, next Tuesday, I can kind of explain those concepts a little bit faster. The lab password. Okay, so let's check out the lab password. Oh, the lab password, I'm just going to type it in the text channel, is 3x3b. Looks like a part 2 of the 3x3i's manga. That's just 2 eyes, not 3. All right, cool. The code for the roll. Aren't you in class when I said that?
Does that mean something's gone?
Negative, Daniel. Negative, Daniel. So is negative the answer, or am I saying negative that negative is not the answer? Or do you think that negative is not the answer, the entire thing is the passcode? Questions to ponder upon. No, that's not my IQ. My IQ is actually much, 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 much lower. Somewhere in between. Maybe it's quantized. It's a quantum thing. So if you ask me on certain days, it is 4. If you ask me on other days, it is 5. So now you have to ask me many, many, many times because the actual value is in between. But each time I answer the question, I can only answer 4 or 5. Yep, that will help you guys get started with quantum computing. All right, so unless there are additional questions that you guys want me to answer, and be recorded, I will go ahead and disconnect, get something to eat, and then I'll be back in 10 minutes. But please try your best to get started tonight so I can answer questions right away instead of having people sending me questions at 11 p.m. the day before the lab is due. Not that it is a problem for me, because when I go to sleep, I just go to sleep. It is a problem for the people who are sending the questions at 11 p.m. It's like, well, I'll get back to you tomorrow because I'm going to sleep now. You can certainly do that. We can all choose to do things differently, Daniel. If it works for you, it's good. All right, you guys have a nice weekend if you don't contact me again tonight. And so don't forget the things that I want you guys to do, okay? Road taking, the lab, and read ahead of me. All right, good night. So I'm gonna disconnect here.